This video explores physics-inspired computation, moving from traditional logic to geometry. We present a unified framework for combinatorial optimization using statistical mechanics and spectral theory. Our overview covers 6 main topics, starting with the computational challenge and why conventional methods fail at scale. We will then discuss reframing logic as geometry. We begin with the computational challenge, examining why conventional approaches struggle when scaling up. The Traveling Salesman Problem illustrates this paradox. Just 20 cities lead to 2.4 quintillion routes, requiring 76 million years for a brute force search. Yet, nature solves similar optimization problems effortlessly, such as bird migration and protein folding. Our thesis is simple: borrow nature's playbook and stop trying to brute force solutions. Classical algorithms, which are logical and exhaustive, often get trapped in local minima. Thermodynamics offers an insight. Systems naturally escape low-energy states by accepting energy fluctuations. This suggests that randomness is not the enemy, and we should harness this principle for computation. Our second section is logic as geometry, where we reframe Boolean constraints as continuous energy landscapes. The core transformation replaces discrete satisfiability, or SAT logic, with a continuous energy function. This shift turns combinatorial search into energy minimization. Instead of searching discrete points, we follow the smooth surface of a continuous energy landscape, letting the geometry guide us. From a statistical mechanics perspective, the partition function z beta encodes all thermodynamic properties. Solutions emerge as the system cools, meaning at infinite inverse temperature, only minimum energy configurations contribute. This means no search is required. We simply follow the energy gradient to find the global optimum. The key innovation is spectral factorization of the partition function. This decomposition connects arithmetic symmetry and constraint topology via the constraint graph Laplacian L. The eigenvalues of L encode the problem's hardness structure. This spectral formulation causes the solver to undergo abrupt phase transitions instead of relying on classical backtracking. Next, we explore phase transitions and hardness, detecting computational difficulty through thermodynamic fracture. We define hardness using the log derivative diagnostic h beta. This function captures how rapidly the partition function changes with temperature. Physically, this relates to specific heat, where peaks indicate phase transitions. Computational hardness is rigorously defined as non-integrability, representing a thermodynamic fracture point, where infinite effort is required by classical optimizers. Section 4 introduces BAHA, branch-aware holonomy annealing. This method achieves exact basin hopping by controlling the Riemann surface. In BAHA, the inverse temperature is a control variable that lives on a multi-sheeted Riemann surface. Each branch corresponds to a different solution basin. Switching branches means exact teleportation between basins, eliminating the inefficient randomness of classical basin hopping. The infinite family of branches from the Lambert W function provides control parameters for navigating the energy landscape. The annealing dynamics follow standard gradient descent on the energy landscape. The crucial step is the branch switching condition. When the derivative of hardness diverges, we hit a singularity. BAHA immediately switches branches, achieving exact, deterministic basin hopping without random restarts or complex temperature schedules. Empirically, BAHA achieved an 84% pass rate across 22 out of 26 diverse nitrogen monophosphide hard problem domains, including TSP and knapsack problems. For the Traveling Salesman Problem, results were 21% better than the target. This demonstrates the superior performance of physics-guided optimization. Our fifth section focuses on multiplicative PINNs, a method for eliminating gradient conflict in physics-informed learning. The classical additive loss formulation for physics-informed neural networks, LAD equals L data plus weighted L physics, creates fundamental issues. This leads to gradient conflict where data and physics objectives fight, stiffness due to scale mismatch, and tuning hell for the weight parameter, lambda. The network ends up fighting itself. The multiplicative fix is simple. L mult equals L data times L physics. This eliminates the need for lambda. In log space, this converts to addition, but the log transformation normalizes the gradients by dividing by the loss. This eliminates gradient domination, ensures scale invariance, and removes the need for hyperparameter tuning. The network no longer fights itself. Multiplicative PINNs achieved a 99.64% PDE residual reduction on Navier-Stokes equations, resulting in a 100,000 times speedup compared to traditional computational fluid dynamics. The method perfectly enforces multiple conservation laws simultaneously, demonstrating realistic physics validation. Our final section discusses the unifying principle, the hidden thesis connecting all these approaches. The fundamental insight is that computational hardness equals non-analyticity of control parameters. Optimization is redefined as guided traversal of phase space, not search or enumeration. This approach relies on physics enforcing consistency, allowing the system to settle into optimal configurations naturally. The production system based on this framework, Navokoj, achieved a 92.57% perfect solution rate on thousands of industrial SAT problems in the Saturday 2024 independent track. It successfully solves extremely hard problems, like 3 SAT at critical density with millions of variables, and provides guaranteed near-satisfiable solutions. This framework is not bio-inspired computing or quantum hype. It is founded on statistical mechanics, spectral theory, and multiplicative calculus. We treat Boolean satisfiability as continuous geometry, embracing gradient flows and phase transitions. By letting the system settle, physics does the work. In conclusion, the future of computation is physics-guided. By combining thermodynamic wisdom, geometric insights, and spectral theory, we stop fighting computational problems and start flowing with them. Let physics do the thinking.
You know, for decades, we've been building our computers on a foundation of pure, rigid logic. But what if I told you that's actually been holding them back? We're about to dive into a pretty radical idea. What if the key to solving our absolute hardest computational problems isn't about writing better logic, but about understanding better physics? Okay, to really get a grip on the challenge we're up against, let's start with a classic puzzle, the Traveling Salesman Problem. Simple, right? You've got 20 cities you need to visit. All you want to do is find the single most efficient route. Sounds easy enough. So any guesses? How many routes could there possibly be? The answer? 2.4 quintillion. Yeah, that's a 2.4 with 18 zeros after it. It's a number so ridiculously huge that even if you had a machine that could check 1 million routes every single second, it would still take you, get this, 76 million years to find the best one. And look, this isn't just some fun brain teaser. This is the very real curse of combinatorial optimization. It's a whole class of problems so monstrously hard that our most powerful supercomputers just throw up their hands and surrender. We've basically hit a brick wall. So, what's the deal? Why do our best traditional methods fail so completely on these kinds of problems? Well, it really boils down to a fundamental clash of philosophies. Okay, so here's the heart of it. Traditional computing tries to be exhaustive. It wants to check every single possibility. But the landscape of solutions is filled with thousands of little traps, or local minima. Once a logical algorithm falls into one of those valleys, it thinks it's found the best answer, and it can't climb back out to find the real solution. The alternative? Borrow from nature's playbook, which solves these things effortlessly every single day. And this, right here, is the big aha moment. Instead of fighting the problem with brute force, what if we just stopped and started listening to what physics has been trying to tell us all along? Now, to be super clear, physics-inspired computing isn't about tossing out your laptop for some new kind of hardware. Nope. It's a totally new way of writing the software. Just imagine a molecule trying to find its most stable state. It doesn't just fall into the first little divot it finds and stay there, right? It uses thermal energy to jiggle and bounce around to explore the whole landscape until it finally settles in the deepest valley, the best possible solution. We can actually teach our algorithms to do that exact same thing. I know this might sound a little out there, a little abstract, but it is already being used in the real world. And the results? They're absolutely staggering. So let's look at 4 ways this is already a total game changer. All right, first up, simulated annealing. This method, which is used in a system called BAHA, brings in principles from thermodynamics. It basically gives the algorithm a shot of heat. This lets it make some weird moves, even ones that look worse for a moment, just so it can jump out of those little traps and get a bird's eye view of the entire problem. It's literally like giving your algorithm a GPS instead of just letting it wander around lost. And does it work? Oh boy, does it work. BAHA has an 84% success rate across 26 different types of these notoriously difficult NP hard problems. Let me tell you, that's not just a small improvement. That is a revolutionary leap in what we can do. Okay, example number 2. A system called Navokoj takes on a different beast, Boolean satisfiability. Now, that's just a fancy way of saying a really, really complex logic puzzle with tons of constraints. But instead of treating it like a rigid puzzle, it reimagines the whole thing as a geometry problem. It's like every rule is a force, and the solution is that one single point in space where all those forces are in perfect balance. So the algorithm doesn't have to search anymore. It just flows to the answer.
And you can see how powerful this shift is when you look at the numbers. We're talking about over 4,000 real-world industrial problems, and it nailed the perfect solution nearly 93% of the time. And on certain types of problems, where other methods just get completely stuck, it hits a perfect 100% success rate. 100!
Number 3 is where we get into AI and machine learning. It's something called physics-informed neural networks, or PINs for short. These AIs don't just learn from a giant pile of data. We actually teach them the fundamental laws of nature, like conservation of energy, as part of their core training. So the AI isn't just guessing what happens next, it understands the fundamental why behind it.
And the payoff for this is just wow. For something incredibly complex, like computational fluid dynamics, simulating airflow over a wing or predicting weather patterns, PINs can achieve a speedup of up to 100,000 times compared to the old way. That's not just doing it faster, that's making the impossible possible.
Okay, and for our last example, we're going to go deep. This is probably the most mind-bending one of all. What happens when you mix the beautiful weirdness of quantum mechanics with plain old everyday logic puzzles? Well, this is where it gets really, really cool. The author of our source material, Sethu Iyer, points to something called the Casimir effect. Now, this is a real thing in quantum physics, where energy can literally pop out of a completely empty vacuum. So the idea is to use that as a kind of metaphor. Instead of painfully searching for one solution among quintillions, what if the right answer could just emerge from this quantum substrate of possibilities? It's a profound, completely different way to think about finding an answer.
Okay, so we've seen 4 incredible techniques. That's the how. But what about the why? I mean, why does changing our whole approach to computing matter so much right now?
Because honestly, the world is facing a mountain of problems that are just too hard for our current computers. We're talking about discovering life-saving drugs, designing revolutionary new materials, untangling global supply chains, and building AI that actually understands how the physical world works. Our old tools just aren't cutting it anymore. These are the challenges where a physics-based approach can deliver the breakthroughs we need.
So what's next? Well, the really exciting part isn't about picking a winner from these 4 methods. It's not like one is going to beat all the others. The real revolution is going to come from combining them.
The future is a hybrid algorithm. Imagine one that can use the thermodynamic smarts of annealing so it never gets stuck. It has the geometric intuition to just flow toward a solution. It's grounded in the real laws of nature thanks to PINs. And maybe, just maybe, it has a quantum perspective on the whole problem. It's about building a complete toolkit inspired by all the different ways nature solves things.
And that really brings us back to the core message of this whole thing. The author, Sethu Iyer, just nails it with this quote. It's a philosophical shift. You stop trying to brute force a solution, and you start allowing a solution to emerge by just respecting the natural structure of the problem itself.
So here's the thought I want to leave you with. What if the next giant leap forward in computing doesn't come from more complex code or even faster chips, but from a deeper appreciation for the simple, powerful rules that have been running our universe all along? It really makes you think. If you had these tools at your disposal, what's the one impossible problem you would choose to solve first?